Hello everybody, welcome back to Unit 7, Lesson 2. Today we are actually getting to perform a test about a population proportion, or a test for significance. We also will call this a one-prop z-test. But before we do that, we want to draw some connections to some of the things that we've already done, namely sampling distribution. So let's go back and take a look at one of our old free response questions from a past unit test, to where you can see that you've actually already done about 90% of the work to answer questions like these. Let's see if you can remember this one. An opinion poll asks an SRS of 500 parents whether they favor sending their school-age children back to school campuses during the COVID-19 pandemic. A local news report states that a majority of parents oppose this idea. I'm going to highlight this. This is some important phrasing here. Now, to investigate further, you find from a random sample of 500 parents that only 48% were in favor of sending their kids back. So, you'll notice this is slightly different, but let's go ahead and investigate what the actual question is here. Do we have statistically significant evidence that less than 50% of the population are in favor of this idea? Well, the great thing is we can answer basically the same way that we answered this same kind of question on the original test. Let's first jot down a couple of things, some notation, right? We had an SRS of 500 parents, so I want to know my sample size is n equals 500. And then we had capital N was going to be all parents of these school-aged children. So I'm just going to write all parents ... here. And then we also see from this random sample, only 48% were in favor of this idea. Now, that is going to be a sample proportion. So that's a p hat. And that's going to be 48%, 0.48. Now, here is this important part here. There's a statement that's been made. What is that statement actually telling us? That a majority of the parents oppose this idea. Less than 50% will support it then. So do we have some evidence to suggest that less than 50% support this idea? Yes, we do have some evidence, but the question is, how convincing is that evidence? Well, that's how we're going to answer this question. And it starts by looking at the characteristics of the sampling distribution of p hat. So let's do that. So we start off by going about this the same exact way, checking these conditions about the sampling distribution of sample proportions. And we'll start by looking at the mean of the sampling distribution of p hat. So remember your notation, that's mu sub p hat, and we know mu sub p hat is supposed to equal p. But we don't know what p is. We don't know what the true proportion is. And you might think, well, let's go ahead and use the thing that we have in evidence, like we did with confidence intervals. And that's actually not what we're going to want to do here. What's actually different about this is we're going to go based off of whatever was stated or whatever was claimed. Because the idea now is we are not making estimates, is we are evaluating claims. So you have to go based off of what is assumed to be true. So we are going to make this assumption that it's all based off of majority. And we know the majority is more than 50%. So let's kind of set our threshold right at 50%. So we're going to state that the average sample proportion should be equal to 0.50 in this case. Okay? That's easy enough to say. 50% of our parents are going to be in support of this idea, 50% are not. The next thing we want to do is know what's the standard deviation of p hat. So sigma sub p hat, you may remember this formula was p times 1 minus p all over n. We've got almost all of those things. We are going to be using that assumed p, but before we can do this, we do need to make sure that this condition is going, or this calculation is going to be valid. So we do have to check our 10% condition before we proceed. Well, it's a good thing we already wrote down some of that information. We know that our sample is going to be less than 10% of our population, that there are definitely going to be more than 5,000 parents of school-aged children. Okay, so our 10% condition is okay. We can go ahead and plug everything in to our calculator here. Okay, so let's go over to Desmos and plug it in, see what we get. square root of 0.5 times 1 minus 0.5, all divided by 500 is going to give us 0.00236, blah, 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 but we'll go ahead and call that 0.0224, rounded to 4 decimal places. So we've got two of the things that we need, right? Remember, ultimately, what we ended up wanting to do was go to a norm CDF calculation. In order to use norm CDF, we needed to have a mean and a standard deviation. We got two things, but we had to know, is it okay to use that norm CDF calculation? And that's where part C comes in. Check that you can use the normal approximation. Is this going to satisfy that normal condition? And remember, we checked that with the LCC, which says that n times p must be more than 10, and n times 1 minus p must be also more than or equal to 10. But again, we're going to make sure we use that assumed value for p, and that's going to be the 0.5. Our sample size was 500, and it's pretty easy to see. I don't need to go to Desmos to know that 50% of 500 is indeed more than 10, and that goes for both parts of this calculation. So yes, we can use the normal condition. Now we can finally answer the question. Okay, remember what we wanted to do was see how likely are we to get a sample like this from our sampling distribution. So we draw out our normal curve and we would do a norm CDF calculation. Now at the center of it goes mu sub p hat, which is supposed to equal p, which as we saw was 0.50, and that's where this bold part here in this part D comes in. If we assume that 50% of the population is in favor of sending that school-age children back. So it's all based off of an assumption, and that is a very important distinction with these significance tests. Now, what do we want to see? Well, what did we get in our sample? How does our sample compare to what we should expect to see based off of this assumption? Well, our sample, p hat, was 0.48, so it was somewhere below the mean, and we want to see how likely were we to get this or even something even more extreme than this. To do that, we would go to a norm CDF calculator. And remember, with this, we plug in our mean, our standard deviation, which we got from the previous part here, 0.0224. Our lower bound goes from negative infinity all the way up to that 0.48. And I do want to make sure I write out what my standard deviation is over here just for kind of completion's sake. And now let's go to a norm CDF calculator, plug in what we got. So let's go ahead and plug in the parameters that we're looking for. Remember, we said that the mean is supposed to be 0.5. And then our standard deviation was 0.0224. And what we wanted to see was how likely we were to get a sample that was less than 48% in favor of this idea. And we can see that it's 18.6% or 0.186. We can see that right down here as a result. Okay? Let's go back and write it in. Now, more specifically, this can be thought of as what's the probability that our sample proportion is going to be less than or equal to 0.48. And we see that there's an 18.6% chance, just by random chance alone, if we assume this is true, to see a sample like this. So the question is, do we really have convincing evidence that the sample is truly less than 50%? So if this value is our answer, this is how likely we are, I would look at this number and say, that seems kind of high. That seems like, you know what, this could have just happened by random chance alone. Maybe it's not really very strong evidence to suggest that less than 50% of our parents are in support of this idea of sending their kids back during the COVID-19 pandemic. Well, this is where significance testing comes in. It gives me a real concrete answer to this question is this so small that I don't think it could have happened by chance alone? Or is it going to be large enough that I'd be like, yeah, this could have just happened by random chance? So now, let's finally get into our notes, and we'll come back and revisit this idea here. So let's really get into it. Tests about a population proportion. This is also known as a one-prop z-test. This is like the calculator language that we would be using, and we might be able to use if we can get to using our calculators. But our essential question is, how do I find this thing called the test statistic, and what does it tell me? Before we get too far into this, we do need to learn some new notation. The first one is P naught. So if you remember from our last lecture, we had an H naught for a null hypothesis, and that's basically what this is referencing. It's an assumed proportion of the population. This is what you're trying to find evidence against, and this is what you're going to use in your null hypothesis and in your alternate hypothesis as well. Now, the p hat, that's your sample proportion. We know p hat very well. It's our evidence that you find from sample that will make you doubt your claim or make it seem implausible. So this is your evidence, okay? So P naught is what you assume to be true, and you check to see if that assumption is correct by doing exactly what we just did, by considering the sampling distribution of that P naught, okay? So it's the same idea that we did in Unit 5. We're just going to have to make things a little bit more formal this time. Okay, and what we are doing is, if we consider that all possible samples are supposed to be based on the sampling distribution of our assumption, our assumed P naught, then we can see, is our sample going to be really weird or very unlikely, right? And the weirder or less likely that P hat is, then the more likely that something is wrong with our assumption. So how do we do it? Well, again, you've done most of it already. The first thing you do need to do is write out any given information, your number of trials, your number of successes, or your sample proportion, and write your hypothesis statements. So your hypothesis statement is going to look like this. H naught, the population proportion, is what I assume it to be, or it's based off of this claim. It's what you doubt. Remember that we are always going to be using an equal sign in the null hypothesis. And then our alternate hypothesis is going to be that it is either going to be less than, greater than, or simply not equal to that assumed population proportion. You're going to use any one of these three inequality statements based on the prompt you're trying to prove. So let's go back up to our previous prompt and do that. So back to our original calculation for that norm CDF condition, we write out our null and alternate hypothesis based off of what we just said. So my null hypothesis is that the population proportion is based off of this claim, is equal to 0.50. Whereas my alternate hypothesis is going to be something a little bit different. Remember, what we wanted to say was we want to know how likely we were to get this sample of 48% in favor. So where is 48%? It's to the left. It's less than. So that means we will say, I think that it's actually less than 50% that are in favor of this. So that's my alternate hypothesis, and I define this value P, where P is the true proportion of parents in favor of this idea. Okay, step 1 is done. What about step 2? Step 2, again, we've already done. It's checking our conditions for inference, but here's the trick. You want to make sure you're using P naught, because that's what's assumed to be true. Everything is based off of that assumption from your null hypothesis. So don't use P hat like we did in confidence intervals. You want to use P naught this time. Okay, this is what's supposed to be true. We do that by checking that random sample. We check the normality condition, which is the LCC, and we do our 10% condition. So again, we've already done these. I'm just going to write them out real quick so I have a formal test of significance all in one place. And there we have it. Conditions done, no sweat. Let's see what step 3 is. Step 3, super easy. This is just like stating your confidence level, except we're kind of looking at those outsides. Instead of looking at what our middle should capture, like that 95%, we're going to look at the outsides. And so we're going to pick some arbitrary number. Usually it's 0.05, it might be 0.1, it might be 0.01, but if you don't have anything to go off of, let's just use this standard of alpha equals 0.05. So I'm going to do that in tandem with this next one, step number 4, calculating the test statistic so you guys can actually see what it is we need to do. The test statistic is like your Z star or your T star. That's what that is. Okay, so the test statistic is actually pretty easy for us to do. It's based off of a Z-score formula. It's your statistic minus parameter divided by the standard deviation of the statistic. Now, our statistic in this case is going to be p hat. The parameter is the thing that we are trying to assume to be true for the entire population, so that's your p naught. And then the standard deviation of the statistic is going to be that sigma sub p hat, or in this case sigma sub p naught, because we're basing everything off of that assumed to be true calculation. So it's over the square root of p naught times 1 minus p naught all over our sample size of n. And this gives us our z-score. So let's go ahead and calculate our test statistic, because we haven't done that yet. So calculating z, I know that that's going to be my p hat minus p naught divided by this square root formula. I've got all the pieces I need. I know what my p hat is. My p hat we had before was 0.48. My p naught, what true is supposed to be true, it's the assumed value. And we divide that by our square root of 0.5 times 0.5 all over our sample size, 500. And when we go to our decimals calculator, we'll see what we get. And there we can see what our test statistic is. Its z is going to be equal to negative 0.8944. And with these test statistics, usually we only have to go to 2 decimal places. So I'm going to go negative 0.89. And that is our test statistic. Z is going to equal negative 0.89. Do not be fooled by this. Some students will think they're done once they found their test statistic. This is only one piece of the puzzle. Let's see what comes next. And now we get back to the stuff that we know, drawing that norm CDF picture, because now we are totally ready to do it. So you draw your norm CDF picture, you set at the center your P naught, what was assumed to be true, and then the cutoff value is going to be considered. Now you could think about it like your P hat. But really what we've done by calculating that test statistic, we want to be able to use a z-table potentially. So instead of thinking about that, the center of a z-table is going to be 0, and then this is your test statistic, your z-score. Okay? And what you're mathematically really finding here is the probability that a z is going to be greater than this value. That's if your alternate hypothesis is using a greater than symbol. If you're in our case, like we saw where we had that shaded region to the left-hand side, then you're finding this, and that's when your alternate hypothesis would be using a less than symbol, or on some occasions, we may be looking at what's called a two-tailed test, because we're not looking at just one tail area, we're looking at 2 tails. And this is when you would be seeing that it's simply not equal to. And you can see the notation that we are using for each one of these and how it differs. Now, we use norm CDF to do this, but you could calculate your z, your test statistic like we just did, and you could use a z-table to find that value that you need. Okay? Ultimately, then, you are just about done. Now you finally find the thing that we need, the p-value, right? When we go to our z-table, we'll be able to find our p-value, okay? Or when you do your norm CDF calculation, you'll be able to do your p-value. So let's get back to our example and see what we got. So we really have 2 ways of doing this. We've already done it one way where we actually got our p-value. Believe it or not, this is your p-value. This is going to ultimately be the value you compare everything else against. Okay? But how did we get there? Well, we did it by doing a norm CDF calculation by comparing the mean of our sampling distribution of mu sub p naught to our standard deviation of p naught, and we wanted to see, compare it to the sample that we got, right? This is exactly what we saw in the drawing that we wanted to try and find. So you've already done this informal thing, and I don't ever want to take that away. You can completely find your p-value going through this process. Or you can find it by calculating this z, this test statistic here, and going to a z table, kind of circumventing and going to a z table, kind of circumventing this whole norm CDF process. So let's find a z table. What we want to do now is find, comparing our z-score that we found, our test statistic, which was negative 0.89, and so I can see near the bottom on the left-hand column in this white row here, there's negative 0.8, and I look at the very top row, the very last one is 0.09. So I find the intersection between the negative 0.8 row and the 0.09 column, and I find 0.1867. Take a moment to try and identify where that is. I'll try and mark it with my cursor here, negative 0.8 in that row. Find how it matches with 0.09. And we can see right here 0.1867, that's our p-value. And what do you know? It's very close to the p-value that we found. So you can say, hence, my p-value is equal to 0.1867, or we can say approximately. We know it's a little bit off just because of rounding error. Remember, we only rounded this to 2 decimal places. And now we compare that to alpha. So over here, I would want to say somewhere that I wanted to let alpha equal 0.05, and now we compare those two things. So my p-value, compare it to alpha. 0.1867, compare that to alpha, 0.05. What do we notice? Well, 0.1867 is greater than 0.05, meaning my p-value is greater than alpha. What do we do now? What do we do with this information? Let's go back and take a look at our notes. Remember what we learned in our last lesson. When you're comparing your p-value to alpha, if your p-value is less than alpha, you reject your null hypothesis. If your p-value is greater than alpha, you fail to reject your null hypothesis. And hopefully you also remember, what does that mean? If you're rejecting your null, that means your alternate must be true. If you fail to reject your null, it means you don't have enough evidence to say that the null is false and the alternate is indeed true. There's still a chance it could be, but we don't have strong enough evidence to say that very convincingly. So let's go back, make our rejection statement, and write it out in context. So what do we got? Since our p-value is greater than alpha, or since 0.186 is greater than 0.05, I fail to reject the null hypothesis. I do not have convincing evidence that p is less than 0.50. In full context, we would say I do not have convincing evidence that p, the true proportion of parents in favor of this idea, is less than 50%. Now, there's a lot of different ways that you can write this out, but you do want to make sure you try to write it in context, where you've defined your variables enough so that it can be interpreted and read in context. But that's it. We have now formally answered this question. No, we do not have convincing evidence that less than 50% of the population is in favor of this, even though we got a sample that was like that. What that means is that our sample could have been less than 50% majority in favor of the idea just by random chance alone. Now, if our sample is more something like 40%, then that would give us a much stronger indication that we were going to have a convincing result. Much stronger evidence to suggest that the entire population is less than 50% in favor of this. It's all based on this p-value and how small that is. The further away this sample proportion is from the mean, then the smaller that area becomes, the smaller the probability is. The smaller that probability is, the less likely it could have happened by random chance alone. And that's performing a significance test. But as you can see, the mechanics of it are very, very similar to the stuff that you've already done. So let's go back and wrap everything up. And you say, but mister, that was a lot. I know. I don't care. You're going to do it anyway. Now, honestly, each of the components that we did are likely to pop up as either multiple choice questions or various parts of the free response questions. So if all you need to do is perform a significance test, there are ways around it. Okay, you can use a calculator like the TI Inspires that we have in class by following these keystrokes here by punching in your assumed proportion, your number of successes, that's a numerical representation like a whole counts representation of your p hat, the sample size, and the sign that you're going to use. Or there are other online calculators that we can use, and I'll show you that. But basically what you need to do here is still show your work. You need to write out that given information in step 1. You need to write out your hypothesis statements that we saw in step 2. You need to make sure that you define what P is, the true proportion of parents that are in favor of this idea. You need to check all those conditions for inference, 10%, random, and LCC. Then you need to perform your test and write out your output. Okay, that includes your one prop z test. That's the name of the test, one proportion that we are looking at, and it's a z test because the z is our test statistic. We write down what that test statistic was, the p-value, and your p hat. Okay, so how do we do one of these calculators with a one prop z test? Let's take a look. So this web applet is going to show you guys what the results will look like in an actual test from a one prop z test calculator. The first thing you have to do is make sure you type in what your stated or assumed proportion is, which in our case it is indeed 0.5, and we were looking at, remember, our alternate had a direction going to the left, so we were looking at the left hand side. Our sample size was 500, and the trick here is you do have to do one extra little bit of a calculation. You have I have data, and the observed x is equal to what? Well, this is how many successes you had. Now, we had 48% success, 48% in favor of this idea. So we have to find out what's 48% of 500. So you can do 0.48 times 500 pretty easily in any other standard calculator, and you'll see your number of successes is 240. So type that in, hit your sample, and you'll get your results. And we can see when x is 240, your p hat is 0.480, your z is negative 0.894, and your p-value, that's the one we really care about, is 0.186. So let's recap what we've learned today. We talked about tests about a population proportion, but we really saw how it was basically the same idea as working with the sampling distribution and calculating the probability of getting a certain sample from a population. It was all just based off of an assumption. So you start off with that assumption and you write out your null hypothesis. That's step number 1. You write out your alternate hypothesis as well. From there, you check your conditions for inference, your random, your 10%, your LCC. From there, you've got a couple of different options, right? You can use all of your given information that you've written down, like your sample proportion, your population size, and those things, to either calculate your test statistic z and find with a z table or a norm CDF calculator your p-value. That's the ultimate thing that you need. Take that p-value, compare it to your stated alpha, your level of significance, and make your rejection or fail to rejection statement. Easy peasy. Now, let's go ahead and put it into practice. But thanks for watching. Have a wonderful day.